Hello students, welcome to the lecture on relational database design, and after this lecture we will be able to learn the following objectives. Understand the concept of relationship design, discuss about null values in tuples, describe the functional dependencies, and understand the concept of multi-valued dependencies. Let us start with database design. Database design theory is a topic that many people avoid learning for lack of time. Many others attempt to learn it but give up because of the dry academic treatment it is usually given by most authors and teachers. Relational database design. The relational database model was conceived by E.F. Cord in 1969, then a researcher at IBM. The model is based on branches of mathematics called set theory and predicate logic. The basic idea behind the relational model is that a database consists of a series of unordered tables or relations that can be manipulated using non-procedural operations that return tables. It is commonly thought that the word relational in the relational model comes from the fact that we relate together tables in a relational database. Although this is a convenient way to think of the term, it's not accurate. The word relational has its roots in the terminology that Cord used to define the relational model. The table in Cord's writings was actually referred to as a relation, a related set of information. In fact, Cord and other relational database theorists use the term relations, attributes, and tuples, where most of us use the more common terms tables, columns, and rows respectively, or the more physical and thus less preferable for discussions of database design theory, files, fields, and records. The relational model can be applied to both databases and database management systems DBMS themselves. Data entry, updates, and deletions will be efficient. Data retrieval, summarization, and reporting will also be efficient. Since the database follows a well-formulated model, it behaves predictably. Since much of the information is stored in the database rather than in the application, the database is somewhat self-documenting. Changes to the database schema are easy to make. Anomalies in databases. Anomalies are inconvenient or error-prone situations arising when we process the tables. Databases are designed to collect data and sort or present it in specific ways to the end user. Database anomalies. Unmatched or missing information caused by limitations or flaws within a given database. They are the data inconsistencies that resulted from data redundancy or partial update. The problems resulting from data redundancy in database table are known as update anomalies. If a modification is not carried out on all the relevant rows, the database will become inconsistent. Any database insertion, deletion, or modification that leaves the database in an inconsistent state is said to have caused an update anomaly. Issues that come about when you are inserting information into the database for the first time. To insert the information into the table, must enter the correct details, must be consistent with the values for the other rows. Missing or incorrectly formatted entries are two of the more common insertion errors. Most developers acknowledge that this will happen and build in error codes that tell you exactly what went wrong. Issues with data being deleted either when attempting to delete and being stopped by an error or by the unseen drop of data. If we delete a row from the table that represents the last piece of data, the details about the piece are also lost from the database. These are the least likely to be caught or to stop you from proceeding. As many deletion errors go unnoticed for extended periods of time, they could be the most costly in terms of recovery. Data redundancy occurs in database systems which have a field that is repeated in 2 or more tables. For instance, in case when customer data is duplicated and attached with each product bought, then redundancy of data is a known source of inconsistency. Since customer might appear with different values for given attribute, data redundancy leads to data anomalies and corruption and generally should be avoided by design. SQL redundancy and DBMS performance issues remain pertinent, and the reader can get a feel for how factors such as poor data. As the cost of data redundancy fell, it became feasible to store data in tables. This eliminated much data storage and provided much more flexible data access. An advantage of DBMS: redundancy is controlled, unauthorized access is restricted. Data redundancy is inconsistency, difficult in accessing data. Data isolation: any such redundancy should be carefully controlled and the DBMS should be aware of it. Data consistency: reduced data redundancy leads to better data consistency. They are the data inconsistencies that resulted from data redundancy or partial update. The problems resulting from data redundancy in database table are known as update anomalies. If a modification is not carried out on all the relevant rows, the database will become inconsistent. Any database insertion, deletion, or modification that leaves the database in an inconsistent state is said to have caused an update anomaly. Informal design guidelines for relational schemas. The informal guidelines to measure the quality of relational schema design are: relational attributes semantics. Design a relational schema so that it is easy to explain its meaning. Do not combine attributes from multiple entity types and relationship types into a single relation. Intuitively, if a relation schema corresponds to one entity type or one relationship type, the meaning tends to be clear. Redundant information in tuples and update anomalies. One goal of schema design is to minimize the storage space used by the base relations. Grouping attributes into relation schemas has a significant effect on storage space. Anomalies are the data within the database. It is the copy of the original data. It needs to be updated in order to avoid problems such as viewing the website. Null values in tuples. If many of the attributes do not apply to all tuples in the relation, we end up with many nulls in those tuples. This can waste space at the storage level and may also lead to problems with understanding the meaning of the attributes and with specifying join operations at the logical level. Nulls can have multiple interpretations, such as the following: the attribute does not apply to this tuple, the attribute value for this tuple is unknown, the value is known but absent, that is, it has not been recorded yet. Having the same representation for all nulls compromises the different meanings they may have. Therefore, we may state another guideline: functional dependencies. A functional dependency, FD, is a constraint between two sets of attributes in a relation. Given a relation R, a set of attributes X in R is said to functionally determine another attribute Y, also in R, written X, Y, if and only if X value is associated with precisely one Y value. Customarily, we call X the determinant set and Y the dependent attribute. Thus, given a tuple and the values of the attributes in X, one can determine the corresponding value of the Y attribute. For the purposes of simplicity, Given that x and y are sets of attributes in R, x to y denotes that x functionally determines each of the members of y. In this case, y is known as the dependent set. Thus, a candidate key is a minimal set of attributes that functionally determine all of the attributes in a relation. A functional dependency Ft. X to y is called trivial if y is a subset of x. Functional depending set S is irreducible if the set has three following properties. Each right set of a functional dependency of S contains only one attribute. Each left set of a functional dependency of S is irreducible. It means that reducing any one attribute from left set will change the content of S. S will lose some information. Reducing any functional dependency will change the content of S. Given that x, y and z are sets of attributes in a relation R, one can derive several properties of functional dependencies. Among the most important are Armstrong's axioms, which are used in database normalization. Subset property, axiom of reflexivity. If y is a subset of x, then x to y. Augmentation, axiom of augmentation. If x to y, then xz to yz. Transitivity, axiom of transitivity. If x to y and y to z, then x to z. From these rules we can derive these secondary rules. Union, if x to y and x to z, then x to yz. Decomposition, if x to yz, then x to y and x to z. Pseudo-transitivity, if x to y and wy to z, then xw to z. Equivalent sets of functional dependencies are called covers of each other. Every set of functional dependencies has a canonical cover. Normalization. In the field of relational database design, normalization is a systematic way of ensuring that a database structure is suitable for general purpose querying and free of certain undesirable characteristics, insertion, update and deletion anomalies that could lead to a loss of data integrity. In a table, an attribute y is said to have a functional dependency on a set of attributes x, written x to y. If and only if each x value is associated with precisely one y value. For example, in an employee table that includes the attributes employee ID and employee date of birth, the functional dependency employee ID to employee date of birth would hold. A trivial functional dependency is a functional dependency of an attribute on a superset of itself. Employee ID, employee address to employee address is trivial, as is employee address to employee address. An attribute is fully functionally dependent on a set of attributes x if it is functionally dependent on x and not functionally dependent on any proper subset of x. Employee address has a functional dependency on employee ID skill, but not a full functional dependency because it is also dependent on employee ID. A transitive dependency is an indirect functional dependency, one in which x to z only by virtue of x to y and y to z. A multi-valued dependency is a constraint according to which the presence of certain rows in a table implies the presence of certain other rows. A table T is subject to a join dependency if T can always be recreated by joining multiple tables, each having a subset of the attributes of T. A super key is an attribute or set of attributes that uniquely identifies rows within a table. In other words, Two distinct rows are always guaranteed to have distinct superkeys. A candidate key is a minimal superkey, that is, a superkey for which we can say that no proper subset of it is also a superkey. A non-prime attribute is an attribute that does not occur in any candidate key. Most DBMSs require a table to be defined as having a single unique key rather than a number of possible unique keys. A primary key is a key which the database designer has designated for this purpose. Normal forms. The normal forms of relational database theory provide criteria for determining a table's degree of vulnerability to logical inconsistencies and anomalies. The higher the normal form applicable to a table, the less vulnerable it is to inconsistencies and anomalies. Each table has a highest normal form, HNF. A table always meets the requirements of its HNF and of all normal forms lower than its HNF, and also a table fails to meet the requirements of any normal form higher than its HNF. The normal forms are applicable to individual tables. To say that an entire database is in normal form N is to say that all of its tables are in normal form N. First normal form, 1NF or minimal form, is a normal form used in database normalization. A relational database table that adheres to 1NF is one that meets a certain minimum set of criteria. These criteria are basically concerned with ensuring that the table is a faithful representation of a relation and that it is free of repeating groups. There's no top to bottom ordering to the rows. There's no left to right ordering to the columns. There are no duplicate rows. Every row and column intersection contains exactly one value from the applicable domain and nothing else. All columns are regular, that is, rows have no hidden components such as row IDs, object IDs, or hidden timestamps. A table that is in first normal form, 1NF, must meet additional criteria if it is to qualify for second normal form. Specifically, a 1NF table is in 2NF if and only if given any candidate key K and any attribute A that is not a constituent of a candidate key. A depends upon the whole of K rather than just a part of it. The third normal form, 3NF, is a normal form used in database normalization. 3NF was originally defined by E.F. Cord in 1971. Cord's definition states that a table is in 3NF if and only if both of the following conditions hold. The relation R table is in second normal form, 2NF. Every non-prime attribute of R is non-transitively dependent, that is directly dependent on every candidate key of R. Boyce-Codd normal form or BCNF or 3.5NF is a normal form used in database normalization. It is a slightly stronger version of the third normal form, 3NF. A table is in Boyce-Codd normal form if and only if for every one of its non-trivial dependencies. X to Y, X is a superkey, that is, X is either a candidate key or a superset of. Summary. Now in the end, let us summarize what we have learnt in this lecture. Designing of relation schemas is based on the conceptual design. The relation schemas can be generated directly using conceptual data model such as ER or enhanced ER, EER, or some other conceptual data model. The goodness of the resulting set of schemas depends on the designing of the data model. While designing relational database schema, the problems that are confronted due to redundancy and null values can be resolved by decomposition. Functional dependencies are one of the most important concepts in relational schema design. They are the special forms of integrity constraints that generalize the concept of keys. A given set of functional dependencies is used in designing a relational database in which most of the undesirable properties are not present. To determine the quality or goodness of a database, some formal measures or guidelines are required. Normalization theory provides the guidelines to assess the quality of a database in designing process. The normalization is the application of set of simple rules called normal forms to the relation schema.